Alright, in this video we'll have a look at the last couple of two-star questions. We left off with question 31 in the last video. Question 32 was a one-star question, so let's move on to question 33. So 33, we've got a set of waves here, and two of them are attached to a fixed barrier, wave A and B, and waves C and D are fixed to free end. Now, they've asked us here to draw the reflected pulses, and we're told that it's a rope, so it's just going to create a wave in there that will perpetuate and reflect back. So the question is here is, well, what direction it's going to reflect back? Is it going to reflect in phase on the same side, or is it going to reflect out of phase? And we need to look at the fixed or free endness there and decide, well, which is it going to be and why. So let's just do our first one. So A looks like this, kind of goes up at a peak and then down, and we've got a fixed barrier here, and direction of motion is this way. So when this wave, this point here gets to here, this point will have upwards motion. And when this gets to here, it's going to have upwards motion or upwards momentum, and that momentum is going to try to push it up, and that means it's going to apply a force. Now, I know we haven't covered forces at this point in time for those who have just started this year, but for every action there's an equal and opposite reaction. We did cover that in grade 10. So yeah, this pushes up, but the wall also pushes down, and because the wall pushes down, that means the reflected wave is going to come back in the opposite phase. It's going to come down looking like this. So if we draw our wall, it's going to end up looking something like that on the way back. Now B is also to a fixed barrier. So, well, we just need to draw the wave inverted, so it would end up looking something like, well, here's our fixed barrier. Let's see, so it's going to start off with, let's see, we're going to be leading with up, and we're going to have a down up, and it looks just like the original wave. Okay, I'll just draw the first wave. Okay, so this direction's going first, so this bit hits first, which means that this section's going to invert and come back first. And we see now here, this upwards is now the leading bit. This upwards bit inverts, goes downwards, a bit off balance. There would be a period of time when this part of the wave is reflected, but this part is not reflected, where they would both be going up, and you'd end up with a really big wave before this part would move out and this part would invert on the way back. But in this case, they both look exactly the same. Okay, let's have a look at C. Now, C and D are both free ends. I'll get to that in a minute. C and D are both free ends, which means they're not going to invert. So we're given a wave like that. It will come back the same shape, just, let's actually make that a bit neater. Goes across, then it goes down steep, back gentle, and then over. And so that means when it comes back, it will gentle, steep, just the motion will change. The thing will still invert horizontally, but it won't invert across the face. D. We've just got a simple arch in this case, so if it's going that way, on the way back, it will look the same. Now, I'm going to put a FET link in the description down below. These are exceptional good use of different physics simulations. They're also available for chemistry and biology as well, probably some, I think, some mathematics as well. And you'll actually be able to play with a wave on a string or a wave on a set of beads. You can do fixed end, free ends, you can do an infinite line, you can fiddle around with frequency, amplitude, that sort of stuff. So if you're confused about these, I would recommend having a look at that. Okay, 34. So we've got another diagram. A heavy spring is attached to a lighter spring and then fixed to a wall as shown. a pulse is sent along the heavy spring towards the wall. First question, draw the pulse that is transmitted into the lighter spring. So heavy to light, it's essentially the same as a free end that we've just seen there. It will transmit in phase. So we've got our heavy spring. That was woeful. Let's try to draw with circles. Heavy spring, and then in our lighter spring, it will be like that. And then we've got the wall. I really can't draw springs too well. It's only asking for what is transmitted into the lighter spring. It's not asking for anything else. Let's mark where heavy versus light finishes as well. So we don't have to worry about any reflection issues. We're just asking, well, what is it transmitting on? It's going to transmit in phase there. If we have a look at part B, it's asking, we'll draw the shape of the pulse reflected from the lighter spring. Well, it's going to be the same as A and B there. We're moving from a, what's the word I'm looking for? It's moving from a heavy area to a light area, and like up here, we went from a heavy area to a lighter area. It comes back in phase. We just reverse the direction. So the bit in the heavy spring will be same phase as before, and then the bit in the light spring, and then we'll have the wall at the end. Okay, and C. What will happen when the pulse hits the wall? So we're asking for a description here. Well, it's going to hit the wall. Newton's third law is going to take over, like we saw with our previous question, and it will come back in out of phase in the lighter spring. And then when it transmits into the heavier spring, again there will be reflection issues where it will reflect back out of phase again, but it will carry on into the heavier spring in phase. So the description, whatever you describe, should mention along the lines of, well, changing phase for changing the wall after hitting the wall. But it's not, then it hasn't really clarified. We'll talk about it through the lighter and the heavier, but it could be a sort of extension and demonstration of knowledge. If this was a B standard question, it's like the difference between a B to a B plus, possibly even an A minus type thing if the result is really well detailed. So there'd certainly be mention of change phase, the light, what would happen at the light to heavy barrier. Okay, these are a couple of points you'd want to talk about. I would especially elaborate on the why. In that case, we're talking about Newton's third. Okay, question 35. So we've got a graph there, and that's figure 13.45. Illustrates a pulse that is moving to the right along a stretched rope at a speed of 4 centimeters per second. Now we've got speed. I'm just going to write velocity because it is moving in a straight line, which means it is the same thing. 4.0 centimeters per second. We could convert to meters, but if I have a look at the graph here, I can see that both axes are in centimeters, so there's no real point at this point in time. All the distances look to be in centimeters, so we could just leave it at centimeters. And we're asked, well, we'll draw the position of the pulse 1 second later. So we've got a speed, we've got a velocity, and we're told that it's 4 centimeters per second. So after 1 second, each of those points are going to go forward 4 centimeters. So let's start with the head of the wave. The head of the wave is E. It's at position 5 originally. So 1 second later, it's going to be 4 centimeters further. So 5 plus 4 is 9. D is at position 4. Add 4 gets to 8. C is position 3. Add 4 gets to 7, and so forth. Do take note, A is halfway between 1 and 2, so it would go to 5.5. So let's draw that. We've got our scales. If that's 9, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're going to have E there, and we need to go up to 8. 1, 2, 3, 4, 5, 6, 7, 8. D will still be at 4. C will still be 8, it's just further across. B is back one more number. And then A is here halfway, but again at 4. And then the last bit will be here at 5. 5, 6, 7, 8, 9. E, D, C, B, A. 4. 1, 2, 3, 4. 5, 6, 7, 8. Okay, and our wave would, let's connect the dots. It's just going to look something like that. Same shape, just move forward 4 centimeters. B, we're asked, well, if A is the point on the rope, and we can see that there, where will it be in 0.5 seconds? So original S displacement is equal to 1.5 centimeters. Call that SI. We want to know, well, what is SF equal to? How far does it go? Or where does it end up? So we need to know how far does it go. And we know that time equals 0.5 seconds. I do apologise, my 5s look like S's. Well, we've got a bit of speed. It's travelling at 4 centimetres per second. And if you think about speed equals distance or velocity displacement over time, but if I take the velocity times time, and sometimes you'll see this symbol delta written in front of the change in displacement, because we want to know, well, how far, if it starts at here, it goes to there, that's going to be the change. We've got our V and T, let's substitute that in. 4 times 0.5 equals 2 seconds, sorry, not 2 seconds, 2 centimetres. So therefore, if I add 2 centimetres to that, SF equals 3.5 centimetres. And all this working out is really not necessary for this sort of question. It should be reasonably intuitive that you're going, oh, okay, well, it's 4 centimetres per second, it's half a second. What's half of 4? Let's add that to it. But this is a sort of formal notation to help you show you're working out. It's not a bad thing to do, but don't super stress about it if it looks like it's way over the top. C, finally, what is the amplitude of the wave? Well, we can read that, it's no different from else. It's just going to be 8 centimetres. Okay. Alright, so let's move on to question 36. So, 36, we've got 2 diagrams here, and we are told that one is at time equals 0 seconds, the other is at time equals 0.2 seconds. We have 2 waves, they look to have an amplitude of about 2 centimetres, and we have a displacement along the x-axis. Note, we don't have time because we had time before. Let's see. So, we can read wavelength, and well, it looks like we're going to have to work out velocity somehow. Okay. Let's go into this. So 36. A. So firstly, what is wavelength? Well, we've got graphs of displacement. Let's just read it off. If we have a look at the graph on the left, a full wave cycle happens in 4 centimetres. The peaks on 1 to 5, so that's 4 centimetres. Troughs are 3 to 7, that's 4 centimetres. Second one, peak is 3 to 7, that's 4 centimetres. Repetition 4 centimetres. Trough 1 to 5, again 4 centimetres. So everything looks to be 4 centimetres. Right. Lovely. So frequency. We want to know, so frequency is the number of waves that pass a point in 1 second. How often the wave happens in 1 second. Now we're probably not going to be able to get to frequency in one go, but we can probably get to period quite easily, because we've got a time here that 0.2 seconds the wave moves a certain amount. If we have a look at that, we see that the wave essentially flips upside down. Or you can think about it, the crest of the wave moves from 1 to 3 in 0.2 seconds. So then another 0.2 seconds would take it from 3 to 5, which would be 1 full wavelength. So if it's moving half a wavelength in 0.2 seconds, it will move a full wavelength in 0.4 seconds, twice the time that we've got there. This is our definition for period. So T, remember, is time it takes for one repetition to happen, okay, one wave to repeat itself. We've got half a wave in 0.2 seconds, so therefore one wave must be 0.4 seconds. Now this we can convert to frequency, and this is why if you look in the question, we've got wavelength, frequency, amplitude, and speed. You can work out frequency from this, but it's a little bit harder to wrap your head around. They wanted you to work out period and then use that to work out frequency. Alright, F equals 1 over T equals 1 over 0.4. That would equal 2.5 hertz. Okay, C, we want amplitude. So now we're a bit easier. Note, really important with these sort of questions, if you're stuck on B, you might sort of give up and go, I can't do the rest. And you certainly won't be able to do D without B. But the next one, A, for amplitude, it's only a C standard. It's just a direct read off the graph. B is more of a B standard sort of type part because you are interpreting data you have to read off the graph, and D's sort of a B standard as well that you have to take two what's what it's unlocking for, 2 bits of data that you've got from different sources and then synthesize it together. So amplitude in this case is just 2 centimeters. We can read that directly off the graph. And D, we want the speed of the wave. Well, we know that V equals F lambda. We've got lambda, we've got F 2.5 times 4 equals 10 centimeters per second. Remember that 4 was in centimeters, so make sure we're using the right units there. Or we could rewrite it as what's what we're looking for, 0.1 meter per second as well. So either would be acceptable. Alright, there's our 2-star questions. We'll get on to the 3-star questions in the next video. Thanks very much for listening, and do check out that link down below, as they do have a lot of really great simulations you can use to help with your study. I'll link you directly to the wave one, but feel free to have a look through the rest. Thanks, guys.